Hi. So with me right here is a past paper that is Math 4119. This is Engineering Mathematics 3. So there are seven interesting questions here, okay, that we're able to go through. But what I'm focusing on in this video is question 3. Okay, so question 3 has four parts to it. That is question 3a to question 3d. So we're going to look at each part step by step, and I'll try my level best to make things as straightforward but clear as possible. So question 3a says, given the function f of x, which is uh, this part right here, we have open bracket x minus pi over 2 close open cotangent x minus 1. So we have to show that x is equals to pi over 4 is a root for f of x is equals to 0. Okay, so part b is asking us to determine the multiplicity of the root x is equals to pi over 4. So what I feel like here, question 3b has already made it obvious that pi over 4 is a root for the function f of x that we're given. But I mean, we just can't make a conclusion from there. We have to show, because the question is asking us to show. We're going to lose the 2 marks that were allocated to part 3a. Okay, so let's work this out. So we are given our function f of x is equals to open bracket, we have x minus pi over 2 multiplied by, we have cotangent x minus 1. So we have to show that x is equals to pi over 4 is a root for f of x, which is that f of x there. So what we are trying to find is that when we substitute where there's x, you substitute with pi over 4, you are supposed to end up with f of x being equals to 0. So meaning you are supposed to have something like f of pi over 4 should give you what? 0. This tells you that pi over 4 is a root for the function f of x. Okay, so to show is just a matter of substituting. So that is going to be like pi over 4 here is equals to, you're going to say pi over 4 minus pi over 2. Then here you're going to say cotangent pi over 4 minus 1, like that. Okay, so here pi over 4 minus pi over 2, you're going to end up with minus pi over 4, because like the common denominator is a 4. So if you have a 4, 4 into 4 is a 1, so you have a pi here. Then minus 2 into 4, it's a 2, so you have 2 pi. So that will give you like minus, you're going to get pi minus 2 pi. That would be like minus pi divided by 4. So we get minus pi divided by 4 right here. Okay, so what about this other portion here? So I'm pretty familiar with the standard trig functions such as sine theta, cos theta, as well as tan theta. Okay, so one thing is that from trig identities, okay, yeah, trig identities, we will know to say cotangent theta or cot theta is simply equals to 1 over uh, tan theta, like that. Okay, so what in this case, what is our theta? Our theta is just pi over 4. So we are saying let me say tan pi over 4, tan pi over 4 is equals to 1, because we are talking about tan 45. Pi over 4 is 45. So you can actually look at this from this triangle right here, like those special angles. So if you are given something like that, so let's say here we have 45, and here we have 45, here we have 1, here we have the square root of 2. So when we say tan 45, because we know that from SOHCAHTOA, tan 45, okay, is simply equals to opposite over adjacent. And what is our opposite? Our opposite is a 1 divided by the adjacent, which is also a 1. So we end up with a 1 right there. Okay, so that's where that 1 is coming from. So it simply means to say, we are going to say cotangent theta is equals to 1 divided by tan theta. We have found that it's 1. So we are saying cot pi over 4 is equals to 1. So we have 1 minus 1, like that here. Okay, so what do we end up getting? So 1 minus 1 is a 0, so it's more like minus pi over 4 multiplied by 0. So that's going to be what? That's going to be a 0. So this confirms that pi over 4 is the root for um, this function f of x that we have right here. Okay, so that was all that question 3a required us to do, and it's pretty straightforward. So for question 3b, it says for f of x in part a, determine the multiplicity of the root x is equals to pi over 4. So when it comes to multiplicity, if I were to talk a little bit about what multiplicity is, in terms of the definition, the simplest definition that I can give is that multiplicity of a root, it just basically tells us how many times a particular root repeats. I mean, how many times a particular root that you have is repeated for a given function, or how many times it repeats itself for a given function. It's more like, let's say you have f of x is equals to let's say x minus 1. Okay, the one of the roots for this like the root for this function here, I can say x is equals to 1, because when I plug in 1 here, I end up with a 0. But let's say I have something like I do this, I square this, of which this can be written as x minus 1. I have x plus 1 here, like that. Okay, so here one thing you observe is that what you plug in here and what you plug in here, it's just more like the root is going to be repeated. So in general, multiplicity of a root just describes how many times that particular root that you have is repeated for a given function. So how do we come up with how do we determine the multiplicity of a root? So what I'm going to do, what I'm going to use is I feel like the most basic method that you can use, that is by using the derivative test approach. So what it means is that when you're using the derivative test approach is you're going to check for the successive derivatives. So if say you have f prime, okay, f prime of x, but of course you have to substitute. Okay, if f prime of the root, allow me to use r for the root, if this is not equals to 0, okay, if you differentiate, then you substitute in your derivative. Okay, in your gradient function you substitute r, which is your root, then what you get is not equals to 0. This tells you to say what you have has a multiplicity. Let me use m for multiplicity. It has a multiplicity of 1. If your f prime, okay, of r is equals to 0, but your f prime prime, meaning your second derivative of r, is not equals to 0, okay, this tells us this has a multiplicity of what? Of 2. In a similar manner, if you have f prime of r is equals to 0, you also have f prime prime of r is equals to 0, but you have that f prime prime prime, which is the third derivative, this is not equals to 0. This tells us that this has a multiplicity of what? Of 3. So in a general, in general, I can say if you have f prime of r is equals to 0, you have f prime prime of r is equals to 0, or you have f prime prime of r is equals to 0, but your f to the m, meaning whatever, that's more like the mth derivative, or let me use n rather. Let me use n of r, this does not equals to 0. You're going to find that your multiplicity is just equals to what your n is equals to at this point. Okay, so this is what we use when we go the derivative test approach when you are determining the multiplicity. So let's look at the function that we have then and see what we are going to end up with. So the function that we have is f of x is equals to x minus pi over pi over 2. Then you have a cotangent x minus 1. So here you can use the product rule. So let's first of all determine the first derivative. So that will be f prime of x will be equals to, so if we use the product rule, I'm going to differentiate this, then keep this one the way it is. So the derivative of this part is a 0, derivative of this part is a 1. So I'm going to write this as cotangent x minus 1. Then I'll say plus. I write this one the way it is, so that would be like x minus pi over 2. So the derivative of this, the derivative of 1 is 0, but the derivative of cotangent x is simply equals to minus cosecant squared x. So that would be like minus cosecant squared x, of which everything here I can write it as cotangent x minus 1. Okay, then minus, you have x minus pi over 2. Then I have cosecant squared x. The minus that was here is the one that I've moved and brought it right there. Okay, so let's do the evaluation. So if we say f prime of r, what is our r? It's our root, which is pi over 4, is equals to, we say cotangent pi over 4 minus 1 minus, here we put pi over 4 minus pi over 2, then multiplied by cosecant squared pi over that is pi over 4. Okay, so cotangent pi over 4, we know that is equals to 1. We already determined it earlier, like this is equals to 1. Then we say minus 1 minus, for this part is minus pi over 4. Then for this part, we know that cosecant, okay, cosecant theta is equals to 1 over sine theta. Okay, so meaning if you say cosecant pi over 4 is the same as you saying 1 over sine pi over 4. So remember, we drew a triangle somewhat like this. So if you have 45 here, okay, and 45, you have 1, you have 1, you have the square root of 2. So sine 45 is basically 1 over the square root of 2. Okay, then you plug it here. So what are we going to have? So it's just more like you're going to say cosecant pi over 4 is equals to, you say 1 over, here sine, we have determined that is 1 over the square root of 2. But remember, this here is squared. Okay, so this is squared, so it basically means even this part has to be squared. So this is going to be like 1 over 2, and this just ends up to be what? Ends up to be 2. So we have a 2 right here. Okay, so that's what we have. So this obviously gives us a 0. Then this negative times negative becomes positive. Pi over 4 times 2, that's going to give us pi over 2. So one thing you observe is that this does not equals to 0. So hence it tells us that this root has a multiplicity of 1, meaning m is equals to 1. This is the multiplicity of that root that we have right there. Okay, so that was all about question 3a as well as 3b. So we basically have about 6 marks to ourselves, 3 marks actually. Then we'll go to question 3c, okay, which says, hence use the modified Newton-Raphson method to iteratively generate a sequence of values that approximate the root x is equals to pi over 4. Use 4 iterations with the initial value of x naught is equals to pi over 6. So this kind of like specified how many iterations we should use. So it makes it much easier. But even when it's open, the number of iterations that you do also determines how many decimal places that you are using for your question. Okay, so how are we going to approach this? So one thing that I believe we are all familiar with is the expression or the formula that we use for the modified Newton-Raphson method. So it's basically x sub n plus 1 is equals to x sub n minus f of xn multiplied by f prime of xn divided by, then here we have, I'll use square brackets, then you have f prime of x sub n, you close squared, minus f of xn multiplied by f prime of xn there like that. If I've made any mistake on these the derivatives, please don't mind. But this is basically the expression that we use for the modified Newton-Raphson method. But there's a catch. We only use this if and only if we have a known multiplicity. Okay, a known multiplicity. But in our case, we know that the multiplicity that we have for that root is m is equals to 1, which is basically a simple root. So what are we going to use? We're just basically going to use x sub n plus 1 is equals to x sub n minus m, which is our multiplicity. And this is what you use if you have determined your multiplicity. Then you have f of xn divided by f prime of xn there like that. Okay, so this is basically what I'm going to be using in this part of the question. So let me just try to bring it up here. So we have x sub n plus 1 is equals to x sub n minus m, but in this case our m is equals to 1, so I don't really have to include it. So here we have f of x sub n divided by f prime of x sub n. Okay, so let's go ahead and do what we need to do. So remember, we are trying to approximate x is equals to pi over 4, and you punch that on your calculator. Pi over 4 is somewhat equals to 0.78 5398163. So for me, you can use, I mean, maybe 6 decimal places, but I find it much convenient to use 5 decimal places. So 0.785398. So when I round off, that's just going to be a 40. So I'm just going to be like throughout the question or the iterations, I'm going to be using 5 decimal places. So this is what I'm trying to approximate. And remember, the question has clearly told us to say our x naught is equals to pi over 6. That's the one that we use as our x naught. It's indicated right here on this part. Okay, so let's begin. So first of all, of course, we have our f of let me just try to write this. We are trying to approximate pi over 4, which is approximately equals to 0.78540. Then our function, okay, our function f of x, we know that it's given as x minus pi over 2. Then we have cot x minus 1. Then our derivative f prime of x is equals to, because here we'll be computing on the derivative part, this is equals to cotangent x minus 1 minus, here you have your x minus pi over 2, then you have cosecant squared x like that. So these two are the ones that we need, because this is just the function itself, then this is the derivative of the function that we have. So let's begin. So if I get my f of x here, I substitute with my x naught, because I'm starting with x naught, which is equals to pi over 6. So if I place pi over 6 right here, is equals to, so I'm going to have pi over 6 minus pi over 2. Then here you have cotangent pi over 6 minus 1. So this is going to give you a value that I'm going to give like with, let me put it right here. So I'm going to use about 5 decimal places, as I said earlier. So that would be minus 0.76660. Okay, then let's compute the derivative. F prime of pi over 6 is equals to, so what do we have? We have cotangent pi over 6 minus 1 minus pi over 6 minus pi over 2. Then we have cosecant squared. Once again, you can write this in terms of sign, like 1 over sign. You put pi over 6 here. So this is approximately equals to, again, I'll use 5 decimal places, 4.92084, like that. Okay, so all you need to do now is to get back to this. So remember, we are using x naught. Our n is equals to 0, because we are using x naught, like n is equals to, that's our first iteration. This is our first iteration. So meaning we have x sub 1 is equals to x naught. What's our x naught? Is pi over 6 minus, we have this part here, because of this negative here and this negative, so that just becomes positive. So we have 0.76660 divided by 4.92084. So this is going to be some value, 0.67939. That's the value that you're going to get. So this is our first iteration right here. So in a similar manner, you have to continue, and you have to continue uh, until you do about 4 iterations, which is what the question is asking. So our x sub 1 is equals to 0.67939. That's what I've determined. Our x2, which will be on the second iteration, if you follow the same steps that I've just showed you that we have done on the first iteration, you're going to end up with something like 0.76444. Then your third iteration, x3, will be equals to 0.78445. Then the fourth iteration, x sub 4, will be equals to 0.78526. Okay, that's what the question is asking us to do. Like, we do 4 iterations, so we're going to end here. If you do up to like 5 iterations, your x5 is going to be equals to 0.785399968, of which you are going to end somewhere here to say 0.78540 if you use 5 decimal places. Yeah, so this is basically how you approach the modified Newton-Raphson method, and we ended up using this one here because we know the multiplicity of the root that we are trying to approximate. Okay, so that was all about part 3c. Let's go to the last part, which is the complex functions. The question is asking us to evaluate each of the following. So the first one that we have is we have open bracket minus I to the power 1 plus that. Okay, so what I'm going to do here is I'm going to try to use the more like the principal branch, is it? Yeah, so in short, here it's just more like my a is the power for z, because it's just more like you have z to the power a. Okay, so it's more like my a is equals to 1 plus I like that. Okay, then what about my z? Z is equals to minus I like that. Okay, so for the principal branch, we're going to say it's log z is equals to natural log of the magnitude of z plus I times the argument of z. Okay, so here it's just a matter of finding the we want to first of all have to find the magnitude of z. So if you look at this z that we have right here, this in other ways can be written as 0 minus 1i, or just I like that. So the magnitude of z is just equals to the square root of 0 squared plus minus 1 squared, which is the coefficient of I, because z is given as x plus iy as a complex number. Then the magnitude, if you're looking for the magnitude of z, is just equals to x squared plus y squared, of which our y is just a coefficient of I. So in this case, we're just going to end up with a 1. What about the argument? The argument of z is basically the angle theta. Okay, and once again, z can be written as x plus iy. Okay, how do we get the angle? We are going to say tan theta is basically equals to y over x. So in this case, okay, in this case, you're going to say theta is simply equals to tan inverse of y over x. But you're not really going to use this approach, because if you look at this part, one of the values, the value for x is 0. Okay, so what we do, we just take it just the way it is here. It's just more like you're trying to approach it in terms of you being able to sketch this. So if you sketch this, okay, so let's say we have this as our x-axis, then we have this as our y-axis. Okay, so keep in mind to say, if let's say, looking at the way we have here, this part is the imaginary part. So on the y-axis, that's why we have the imaginary part. In the x-axis, that's where we have the real part. But if you look at the way it is here, it's negative. So meaning it's down here. Okay? Because this part is either is pi over 2 or minus pi over 2. So meaning even this one is either is minus pi or pi, like that. It's more like, let's say z was equals to 1, meaning it's z is equals to 1 plus 0i. So you're not really going to consider what's happening in the imaginary axis. You just look at what's happening in the real axis. So if it's positive, meaning your angle is what? Your angle is pi, like that. Okay, so in this case you have a 0 here, so you're not really focusing on the real part, because the real part is a 0. So just focus your attention on the imaginary axis, of which is this one here. But which one you decide depends with the sign that you have here. Having the sign negative, so it basically means the angle that you have is what? Minus pi over 2. So our argument z is basically equals to minus pi over 2. So let's go ahead and finish this up. So we're going to say log z is equals to natural log of magnitude of z, we have found that is 1. Then we say plus, we say I. The argument of z, we have found that is minus pi over 2. So natural log of 1 is equals to a 0. So we end up with log z being equals to minus I pi over 2. Okay, so the question is that, are we done? No, we are not yet done. So one thing that you have to keep in mind is that when you have z, okay, when you have z to the power a, this can be written as e to the power a times log z there, a times log z. Okay, so another thing again, when it comes to e to the x plus iy, this can be written as e to the x, you have open bracket, you're going to have cos y, okay, plus I sine y, like that. So what are we going to do? First of all, I'm going to work out this part. So I'll come and say z, what is my a? But I don't really have to put it there. So that would be like e to the power a. What is our a? Our a is this one right here. So it is 1 plus I, like that. What is our log z? We have already determined our log z, which is this one here. So that is going to be minus I pi over 2. So this can be like e to the power, if you distribute this, multiply this by 1, multiply this by I. So I times I, more like I squared, is equals to negative 1. Okay, so that negative 1 that you get when you multiply this I times this I, that's going to multiply this negative here, so that's going to be positive. So I have pi over 2. Then I have minus I pi over 2 times 1 is just minus I pi over 2, and this is equals to, now I'm going to pick it from this part. Okay, so this is going to be equals to, I'll say e to the power x. Our x is the real part, which is this one. Okay, so which is pi over 2. You open the brackets here, then you say cos, what is our y? Our y is the coefficient of I, and in this case it's minus pi over 2. But because cos is even, okay, we're just going to have to put pi over 2 there, like that. Then we say plus. So maybe before I even continue here, you observe to say you're going to plug in minus pi over 2, but sine is an odd function, so this is going to be minus I sine pi over 2. So meaning the product that you're going to get here, yes, it's a positive, but because of the presence of this negative here, is going to end up to be negative. So I just have to put it right here. Okay, then I closed like that. What is this going to give us? So for this part here, this is a 0. Okay, it's more like you're saying cos 90. Cos 90 is a 0. What about sine 90? Okay, sine 90 is basically a 1. Okay, so it's 0 here minus you have I times 1 like that. So it's just basically minus I times e to the power pi over 2. So that's just going to be like minus I times e to the power pi over 2, and this is our solution right here. Okay, so let's look at the last part of question 3. So question 3d2. Okay, we have e to the power 3 minus I pi over 3. So we have e to the power 3 minus pi uh, I pi over 3. So once again, I know to say e to the x, I mean e to the x plus iy. I can just write this as e to the x. Then we have cos y plus sine y. There's an I here, by the way. So I'm taking this route because the question is just asking me to evaluate. I don't have to start taking logs. Okay, so it's just asking me to evaluate. Then this is the route that I'm going to take. So here we are going to say it is e to the power 3. Then open bracket, we are going to have cos pi over 3. I don't have to worry about the negative because of the nature of a cos function. Then I'll say minus, I'll say I sine pi over 3 there like that. Okay, so this will be equals to e to the 3. So what is cos pi over 3? Pi over 3 is basically a 60. Okay, is a 60. So if, let me say I use some special angles here, I don't want to use decimal places. Okay, so if we have 30 here and we have 60 here, then here we have 1 2 and square root of 3. So cos 60 is 1 over 2. Okay, so here we have 1 over 2 minus I. So in place of sine 60 is root 3 over 2. So that's going to be root 3 over 2 like that. Okay, so this right here turns out to be my answer, which is e to the 3 per 1 over 2 minus I pi 3 pi square root of 3 divided by 2 like that, and this is my answer. Okay, so this is basically what question 3 was asking us. Okay, so it seems a little bit long. I mean, I've taken about 30 minutes because I'm explaining. So I believe just on your own, you are not supposed to take more than 15 minutes doing this question. I can say myself, if I was to judge here, I can say you can take about a minute, 1 minute doing question 3a, maybe about 1.5, okay, 1.5 minutes doing this other question 3b, or maybe just for good measure, let me make this 1.5, let me make this 2 minutes. Then question 3c, I would allocate maybe about 6 minutes. I don't know, I'm not doing this because there's 6 marks. Then this one, all of them, maybe I can pick about 7 minutes. Okay, so you find that if you say that's going to be 8 plus 7 plus 1.5, you're answering this question in about 16.5 minutes. Okay, which I feel like is fair enough. You can even answer it in time less than this because this exam is about 3 hours. Okay, 3 hours. In that 3 hours that you have, you are supposed to answer 5 questions. Okay, so if I say from that 3 hours that I have, I've used up 16 minutes to answer one question, or rather let me just say 15 times 5, 15 minutes times 5, like each question, you're going to find that you still have some hours, I mean some minutes that are remaining that you can allocate to questions that are a bit longer compared to the others. So when you're approaching certain questions, make sure to say on those questions that you are very sure to say you know them, like fully know them, try to be as fast as you can so that at least you save some time for other questions that might a little bit be long, because there are always those questions that are longer than the others. Yeah, so that will be all in this video. Thank you very much for watching.